Chapter 4, Classification. In this chapter, we're going to learn two new algorithms, K-nearest neighbors and multinomial logistic regression. Along with that, we'll also learn a lot of new concepts. So if I were to summarize this entire chapter in one line, it would be a classification algorithm is used for situations when your dependent variable, the y, that the one that you're trying to predict, when your dependent variable is an unordered finite list of categories. So when your y, the variable that you're trying to predict, is a category, it's a list of few outcomes, and there is no relationship between those outcomes, then it's a classification problem. Let's say you want to predict whether a given email is a spam or not a spam. There are only two outcomes. It can be a spam or it cannot be a spam. So that category is fixed. It's unordered and it's finite. There is nothing that says, oh, spam should come first and then not spam should come second. You could change and have any order. And it's a finite list of those outcomes. And it's a category. Another example could be when you have a credit card transaction and you want to detect whether it's a fraud or not a fraud. Then that's also a finite list of outcomes in your y-dependent variable. And it's a category. There's no like third or fourth thing that you have. But let's say you want to predict the weight of a mouse based on various characteristics. Now that is not a category outcome. It could be a continuous variable. The weight could be 1.1, 1.2, 1.4. It could be 2.1, 2.111. So you see, that's a continuous variable. And so it's not a category in that case, in that example. So if we understand this one line, then I think we'll understand when should we use classification in the right way. So when your dependent variable y, that the variable that you're trying to predict, is a fixed category, unordered list, finite list of categories, then you use a classification algorithm. Yeah, so I've given various examples here: spam, not spam, fraud, not fraud. If you want to predict what ice cream flavor a person likes based on various characteristics, and there are a fixed set of flavors, those are examples. Yeah, so that's classification in a nutshell. When do you use classification? So there are two types of machine learning algorithms, broadly speaking: supervised and unsupervised. And classification is a supervised learning algorithm, right? It falls here. But what do we mean by these two? So it's important to just briefly understand these two concepts as to what is a supervised versus an unsupervised learning. There are many key differences, but the one that's really helps summarize this is supervised learning uses labeled data. That algorithm uses labeled data. Labeled data is basically data which has right answers. So if your algorithm can train on, let's say, certain past emails, if it's the spam detecting algorithm, and if it can train on certain emails and some human has put in right answer that says this email is a spam email, and it can learn based on humans' right answers or those labels, then that falls under supervised learning. And classification, along with regression, is a supervised learning algorithm. So you need to know what is this type of, where does this fall? And so the very first one in this is K-nearest neighbor algorithm. So far we have covered 10 different algorithms. This is the 11th one in this book. So in a sense, what does this K-nearest neighbor do? How would you classify, let's say, a new data point? Yeah, that comes in. How do you classify whether this belongs to this red bucket or to this green bucket, right? It's a new data point and you're trying to find out where does this fall. So what do? You calculate distance. the first step is you for this new data point, you find out like what are the k nearest neighbors from this new data point. So how do you do that? You don't know, like I can see this and I can say, hey, I just want to look at these nearest ones to find out which one is nearest. But the computer can't see this in this XY plot. So what does the computer do? The algorithm will have to calculate distance of this yellow point with all of these red points and with all of these green points, and then figure out how to sort them, because it doesn't know where it stands. So it has to then compute and find out the distance from all of these points, and then find out, okay, which are the shortest ones that I have, right? And there's a threshold in this case. Hey, look at three nearest neighbors. So k equals 3 means 3 nearest neighbors. So you can quickly realize that, hey, we need an odd k, right? So it can't be 2 nearest neighbors, because it could very well be that there is 1 red and 1 green. So you need an odd to break the tie. And you can quickly realize that, hey, if the complexity gets really out of control here, because you have to, for every data point that you want to classify, you have to find out the distance from each of the other data points. So it's very computationally heavy, but it is very intuitive. The algorithm is very intuitive. It finds out, calculates the distance, and it knows which are the nearest ones. Yeah, so that's a very easy way to classify whether this bucket, in this case, this yellow bucket with 3 nearest neighbors, the 3NN, this is also called as KNN, which is k nearest neighbors, or in this case 3NN, which is 3 nearest neighbors. In this case, the 3 nearest neighbor algorithm says, hey, you are closer to 2 out of these green triangles than this 1 red star, so you better be classified as green. So that's the classification. That's as simple as that. Find out the distance of this new data point from all of these data points that exist, and then have a cutoff, in this case 3NN, and then 3 neighbors. Look for the ones that are maximum, and then assign yourself to that classification. So that's KNN, k nearest neighbors algorithm. But this is expensive, as we saw. Is there a cheaper way to do it? Yes, there is a cheaper way, but that builds on top of this binary logistic regression algorithm that we learned in chapter 2, right? You remember the spam filter? So what if we could use some of these characteristics of binomial logistic regression and use probability? Even here, it classifies into discrete set of classes. But what if there are several classes? So this is an example of classification, right? And what if we could use probabilities, which is basically a count of all of this data that we have, and what is the probability of certain data being in certain category versus in another category, and then we can find out the cost of each of these cost of these decisions. Then we can use classification. So if we can use the power of probabilities, and if we can add to it the cost function as to what is the cost of each of those actions based on those probabilities, then we can build a classification algorithm. So how we do this? Let's quickly recap. What is the type 1 error? If you remember, type 1 error is false positives. So if you predict a disease, in this case, let's take a disease. If you predict a problem or a disease when there is no disease, that's a type 1 error. You just predicted a problem when there was none. So that's a false positive or type 1 error. And then there's type 2 errors, which is you failed to predict a disease or a problem when there is one in reality. There was a problem, but you failed to detect. So there's false positives, false negatives, type 1 errors, and type 2 errors. Because each of these algorithms that will be built on probabilities will come with these type 1 errors and type 2 errors. So it's important for us to know, if you're going to use algorithms based on probabilities and cost, each probability comes in with type 1 errors and type 2 errors, and has its own sensitivity and specificity. So sensitivity is like ability to detect a disease. In this case, if you go for the very first time and you're trying to get screened for, let's say, cancer, then it's highly preferable to have an algorithm or a machine that is highly sensitive. So you prefer high sensitivity. And when you go for a follow-up, you prefer high specificity. And they don't, this is ability to detect health, this is ability to detect disease. But if you see, these are all connected. So we saw false positive rate, which is false positives here, and then false negatives. And the sensitivity is true positive upon true positive plus false negative. And specificity is, true negative about true negative by plus false positive. And then there's this index that we can use, Jordan index, right, which is sensitivity plus specificity minus 1. And if we recollect all of this, and if we can know what are the trade-offs, right? Like, hey, for a given specificity, we'll get certain sensitivity. And if we can use that to our advantage, then we can say, hey, for my business use case, I can be okay with this sensitivity and with this specificity, and this is the cost of that sensitivity, and that's how I'm going to classify. Then that's one way. So that's the intuition here. So let's look at how multinomial logistic regression actually uses all of these probabilities and costs and all of these trade-offs associated with it. So, and we'll make it very concrete. Let's say you're a loan officer and you're trying to detect whether this new person that comes in, should you give them a loan or should you not give them a loan? So you're trying to predict in some way whether there is a probability of default is high, right? If the person will default or pay back the loan in full, that's something you're trying to predict, and there's a cost to your business. So step one, what do? Step one is you list out all of your outcomes. In this case, there are only 2 outcomes, right? But there could be 3 or 4 outcomes. Step one, list out all outcomes. In this case, the 2 main outcomes could be the person defaults, doesn't pay you back, or the person pays you back, right? And so the loan is returned in full. And so for each of these outcomes, you need to write down what is the cost. When someone defaults on certain loan amount, what is the cost to your business when they don't pay you back the money in principle? Once you know that, and you have certain historical data of your previous loans that you have granted, step 2 is for you to run a binomial logistic regression that we just learned in chapter 2 on all of your historical data. What does this give you? This gives you an ability to predict, which is probability. It gives you, the model builds prediction capability based on historical data, and this binomial distribution logistic regression will help you with a probability. They say, hey, I have learned based on your historical loan giving data that these are the probabilities. But remember, these probabilities come in with their own true positive rate and false positive rate. And so you have to know what is that true positive rate and false positive rate. So once you run that step 2, you run this algorithm, it will also tell you the probabilities or the ability to predict a default or a non-default, but it also give you the FPR and TPR, which is your true positive rate, false positive rate. And once you know that, and if you may say, hey, this sensitivity, and you can also calculate sensitivity from true positive rate, and you can calculate specificity, 1 minus specificity with false positive rate. Once you do that, you can actually plot this something like this, right? Which is sensitivity over 1 minus specificity. So true positive rate versus false positive rate. Once you do that, you will get this trade-off curve. It says, hey, these are your trade-offs. If you require high sensitivity, ability to detect that there is a problem, versus ability to detect whether everything is fine, loan default, no default, then you will have a cost associated. So you can say, hey, now that for your probability that you're telling me algorithm, hey, these are your true positive, false positive, or sensitivity and specificity rate, you can adjust it. You can say, hey, no, my expected loss tells me I need you to be more specific or more sensitive. So you can change your algorithm to say, hey, I need a higher cutoff. And so you can make it more sensitive or more specific. Once you do that, you can then choose what cutoff works best for you, which is basically any point in this curve. But there's this really good index called Uden index, which is basically the point that is closest to this leftmost point. So this is the closest distance, and that gives you the best trade-off between sensitivity and specificity. Yeah. So that's one way in which you can run your multinomial logistic regression to say, hey, first, find out all the outcomes and the cost associated with those outcomes. Second, then you make it first learn based on your historical data, the probability or the ability to predict, and then make it give out your specificity and sensitivity numbers. Maybe it comes here. Then you realize, oh, I need a higher cutoff. So you increase your probability threshold. Say, hey, I want a higher cutoff. And so basically what you're choosing here is the right cutoff. At that cutoff, you say, hey, this is a default. So a classification in this case is a cutoff probability that you are comfortable with. You are choosing a point here for a given sensitivity and specificity that says, hey, if it's below this point, this is a default for me because I can't bear the cost of this business. So in a sense, your classification algorithm's learning from you what is the right cutoff probability, at which point you want it to say it's a default or a no default. So that's multinomial logistic regression. It's algorithm 12. Yeah, that's actually it's not the 12th algorithm. It's actually built on top of the binary logistic regression. This is multinomial, meaning it can have multiple outcomes. In binary logistic regression, there are 2 outcomes. Here you could say, hey, let's say we were talking about this example of predicting which ice cream flavor someone likes. Then you can say, hey, there could be strawberry, chocolate, vanilla, or 4th or 5th. But in this specific example is still binary logistic regression, and multinomial logistic regression is a generalization of binary logistic regression. So hopefully you get the concept or the intuition behind how you can marry the probabilities with the true positive, false positive, and expected loss to minimize the expected loss, and then say, hey, this should be classified more aggressively or less aggressively. Yeah. So that's the intuition behind multinomial logistic regression. The book also, in the last 2 pages of this chapter, goes into Mapreduce, which is algorithm 12 slated in this book. This is a very complex topic, but let me give you a high-level intuition. In a sense, let's say you're trying to do a word count. You have a document and you want to count how many times a given word is present in this document. It's a very simple example in this case, but you could also imagine you want to, in this case, it's a count, right? You're trying to count. But what if you wanted to count, and what if you wanted to build coefficients of your various independent variables, right? You could then have your independent variables here and the coefficients being computed here. So it basically takes an input, in this case, counting how many words are in this text, and outputs this file that says, hey, each of these words, how many times it came in. So in a sense, Mapreduce is trying to do 2 things. It's trying to, it has this mapping step wherein it distributes or splits work. And then it has this reduction step wherein it can do things in parallel. As you can imagine, see here, it's adding all of these in this one segment. This one computer gets all of the words that have Hadoop equals 1, right? So if this one computer, right, it uses a set of computers. Each of these are like, let's say, computers trying to do this. It actually is able to parallelize and distribute the work. See, Hadoop is being counted only by this machine and not everyone else. So Mapreduce, in a sense, helps you to distribute work across several machines and do things in parallel, right? So that's this algorithm. So you could imagine this word count could be replaced with computing coefficients for your independent variables, for your various algorithms. So this Mapreduce framework, in a sense, allows us not just to do things in parallel, but also in a distributed fashion. So in parallelization in algorithm is if we can compute certain probabilities, let's say in parallel. But then parallelization also requires access to all the data all the time. But a distributed algorithm is when it has all the data that it needs. It doesn't need the full data set. In this case, this machine here has all the inputs of all the places where Hadoop comes in, right? So that's a distributed nature of this algorithm. So if we can build an algorithm in such a way that they can be distributed so that the coefficients can be built across multiple machines, that's what this framework allows us for. Because if you remember, even in KNN, you had to find out distance of a given data point with all the data points in the data set. That's expensive. So what if you could do that in parallel and in a distributed fashion, wherein you could do that in such a way that you don't need the whole data set, but you can still compute. So Mapreduce does that. It's a distributed algorithm and computes all coefficients. In this case, the coefficients here are like the count, but it could be a complex coefficient with a lot of compute involved. And Hadoop and Spark, these are also mentioned in the book in the last page of this chapter in passing, but these are the technologies that could be like a book in itself. So these are, but knowing that, hey, these Hadoop provides this infrastructure for Mapreduce, Spark adds to this, various things for a nearline processing and machine learning capabilities on top of Hadoop. So it does a lot of analysis parts as well. Then you can, compute all of these coefficients and have machine learning algorithms built on top to do the analysis. So that's what this chapter ends with. But in a sense, if you were to take this one thing out, Mapreduce with Hadoop and Spark allows you to build these coefficients of your classification algorithm or your regression algorithm in parallel, in distributed fashion, right? Wherein it's happening in parallel and in computers across the world, right? In the cloud. So that's the overview that the chapter left with. It's a pretty detailed topic, but just remember that these allow us to do things in a much highly compute intensive workloads in a much more efficient way. So if you have questions, I've covered a lot of this in high level detail and abstracted a lot. There may be a lot of questions you may have. So how does this really help, or any specific parts? Add them in the questions below. I'll also paste in the description the link to the slide deck, wherein I will keep adding questions that you have, follow-up questions, and I'll try to answer in that slide as well live, and we can learn from each other. Yeah. So in this chapter, we finished chapter 4, the intuition behind classification algorithms. We learned 2 new algorithms, KNN, K nearest neighbors, and we also used the binomial logistic regression, a generalized version of it called multinomial logistic regression, understood how probabilities are used to make it more compute easy, and also found out ways to further make it better for compute by using distributed algorithms that can run across machines through Mapreduce in Apache Spark. All right, thank you.